Before we talk about ratios, let's talk about the most basic topic from algebra, linear equations, and also what problems based on linear equations. Let's look at a question. 3 more than 5 times a number is 33. What's 10 times the number? Now, most of us know how to solve this, but bear with me for a couple of minutes. I just want to take you through the steps. When you get a piece of information like this, we convert that into an equation, right? There's a number, there's 5 times of the number, and then there's 3 more than 5 times that number is 33. This is what you usually do. That sentence will contain a subject and a verb and an object. Usually linear statements that translate to linear equations are going to be like this. You have a subject which becomes the LHS, the verb is the equal sign, and the object, whatever is there, will turn up on the right hand side. It's a pretty straightforward process converting a statement to a linear equation. And once you have that equation, what do? We remember all the steps back from high school. 5x is therefore 33 minus 3 is equal to 30. And then x is equal to 30 by 5 is equal to 6. So we found the value of x, which is what I assumed as the unknown number. And then they're asking what's 10 times the number. So that's 10x is equal to 60. So the answer to the question that they're asking is 60. The unknown number is 6. Now we know how to do all of this. Just to recap what you may have learned in school. This step of taking the plus 3 and putting it on the other side as a minus 3, that step is called transposition. We would say that we transpose the 3 to the other side. And then this step of taking the 5 from the 5x, 5 into x, 5 in the numerator, you take it to the other side, it goes to the denominator, and that step is called cross multiplication. And you may remember why they work. It's because of something known as the additive inverse and the multiplicative inverse. So if you have 5x plus 3 is equal to 33, I'm just going to move that a bit. You can add the same thing to both sides of an equation and the equation would still hold. So the thing to do is put a minus 3 here and a minus 3 here. And why am I putting a minus 3? Because it is the additive inverse of the plus 3. They cancel each other out, giving you 5x plus 0, 0 being the additive identity, and that is how you get 5x is equal to 33 minus 3, 5x is equal to 30. Transposition works because of the additive inverse, and putting the additive inverse of a number next to it gives you, they cancel each other out and they give you 0, which is the additive identity. And then of course the next step is you can always multiply both sides of an equation with the same quantity as long as it's not 0, and you put a 1 by 5 into a 1 by 5 into. And this 1 by 5 is the multiplicative inverse of the 5. And when you put them together and multiply them, you get 1, which is the additive identity. And the the multiplicative inverse. You put them together, you get the multiplicative identity, which is 1, and that is, and the multiplicative inverse is why cross multiplication works. And now you get x is equal to 30 by 5, which is 6. So linear equations usually have, it's solving a linear equation is only a matter of transposition and cross multiplication. You may have to do them more than once, you may have to do only one of the or the other, but usually these are the only two steps involved, and the reasons why they work are the inverses. Now I'd want you to ponder about what you would do with this problem if you didn't know formal math, which is basically just symbolic logic? Would you be able to reason out the answer? And I think yes. You would reason it out like this. We're told that 3 more than 5 times a number is 33. So we add some operations and then we added 3 to the result and then it became 33. If that is the case, can I not reason and say that before adding the 3 we had 5 times the number is 30, and if 5 times a number is 30, before multiplying the 5 you would have the number is 6. Notice that it's the same thing that we did with the equations. The equations are analogous to this reasoning right here, this verbal reasoning right here. The advantage of using the symbolic logic is that it's precise and concise. It shortens. It's way shorter than saying 3 more than 5 times the number is 33, therefore 5 times the number is 30, therefore the number is 6. It shortens it without losing any of the information. That's why I say it's precise and concise. You'll see that in more complex examples, it might not be possible to reason it out in sentences. It is possible, but it's very painful to do that. And that is the advantage of the symbolic logic. It speeds things up. You'll notice this not only in math but also in the logical reasoning section, where symbolic logic speeds things up. Now, another thing that I want to point out is the number was 6. How did we get to 33? We did into 5, 30, or that is how we got to the 33 that's given to us. The known is the 33, the unknown was 6, right? How did we get to the 33 that they gave us in the question? Step 1, multiply by 5 gets you to 30. Step 2, add 3 takes you to 33. And how did we go from the known to the unknown? We were given the 33 and we're tasked with finding the 6. We first subtracted 3. Notice that it is the inverse operation of the plus 3. That took us to 30, and then we multiplied by 1 by 5. It's the inverse operation of the into 5. That's how we got the 6. Notice that what we are doing is the inverse operation in the reverse order. Very nice insight to have, and there are certain questions that are solved much easier with this insight than by actually framing the equation. So I thought I'd point it out. Let's stay on this example and talk about the 3 steps that are always involved when you solve a word problem. You have some statement or some story, and this one is a very simple, it's one sentence giving you information and one question after that asking for some information. But anyway, you will have some word problem, some statement, some story, and then you frame it and you get an equation. It could be a linear equation, it could be simultaneous linear equations, it could be quadratic, it could be anything. But that step is called framing. What you did here is the framing, and at which point you get an equation or a family of equations, and then you solve it. When you solve it, you get the values of whatever unknowns you have defined. Here I've defined the unknown number that they're asking. They've mentioned an unknown number. I've defined that unknown number as x, and solving the equation or the family of equations gives you the value, which is what I've done here. But then that value is not the answer. They're asking you what is 10 times the number. So I have to interpret that result to get my solution. what are they asking for? They're asking for 10 times the number. So I have to interpret the fact that x is 6 to tell them that the answer is 60. And this is basically what you have in any word problem. You have to frame it, you have to solve it, then you have to interpret your solution in terms of what is the story, what are they asking. And you'll see this in pretty much every word problem. That was the last step. X was 6, but my answer was 60.